So here's a very quick walkthrough of my 14 principles for practical programming that I blogged about quite recently. I'm going to talk about each of these in turn, give you some examples of this where it's relatively easy to track down, give you some of the supporting research as to why these are likely to be effective principles to follow. So here we go. So the first of these is this idea of keep the big picture in mind, but also focus on the details, which is a particular thing which we have in computer science, where yes, the level of detail of where the colon is, what the particular syntax of the line of code is, what that particular line of code does matter. But you also have to bear in mind the whole big picture of what's the purpose of the program that I'm writing there. And believe it or not, Jeanette Wing sums this up beautifully in one of the very early presentations she gave about computational thinking. Her understanding of this was still emerging at the time, but she emphasized abstraction as one of the twin pillars of computational thinking. Computational thinking is operating in terms of multiple layers of abstraction at the same time, thinking about, yes, the user interface, but also the underlying code, thinking about the underlying code and how that works on the particular machine. And this multiple layered model of how computer systems, how software works, is central to our discipline. And this idea of different layers of abstraction, that we solve this particular problem relying on the solutions that others have provided to the much more fundamental problems, to the building blocks of that. It's turtles all the way down. She also, of course, emphasizes automation here. And my worry is that in much of the more recent presentations on computational thinking, we've moved away from automation, this idea that our particular solution to the problem is something that can be automated. I don't think she puts it particularly clearly on the slide deck here. The picture I always have in my mind for this is playing video games, and Stephen Johnson puts it so well when he talks about playing Zelda and the levels of detail in the particular objectives that you have when playing a game like that. I just draw your attention to his final paragraph here of the bit I captured for your slide, called the mental labour of managing all these simultaneous objectives, telescoping, because of the way the objectives nest inside one another like a collapsed telescope. I like the term as well because part of this skill lies in focusing on immediate problems. How do I debug this line of code? While still maintaining a long distance view. What is my program going to do? You can't progress far in a game or indeed in coding if you simply deal with the puzzles you stumble across. Big picture as well as detailed view. And I think we have that really within the sort of way we think of the cognitive load of our subject, this idea of both the semantics and the syntax. Remember Wing's multiple layers of abstraction there. And you have to have how you're solving the problem, what I would see as computational thinking, as well as the expression of that in particular code, so how we actually get the machine to do that. And Schneiderman and Mayer's paper from 1979, that's a while ago now, isn't it, says that actually the way you learn these things are quite different. The multi-level structure of semantic knowledge through meaningful learning, giving a purpose to the programming that we're doing, is replicated in the multi-level approach to the development of internal semantics for a particular problem. The syntactic knowledge, largely acquired by rote learning, is compartmentalized by language. Okay, so yes, I am learning the syntax of Python, but I'm also learning how to solve all sorts of problems in this particular class, I guess. Semantic knowledge is essential for problem analysis, while syntactic knowledge is useful during the coding or implementation phase. Interesting distinction there, don't you think? And I worry, of course, that much of what we do in introductory programming, introductory Python courses, is focus on the syntactic knowledge and don't really start to address how are you trying to solve a problem? Yeah, what problem are you trying to solve? How are you going to go about that? Lister's great paper says that you start by reading examples of what other people have done. The reading code comes before writing code, that the problems that novice coders, novice programmers have when learning to program are mainly due to their inability to reason about code that others have read. It's not their problem-solving skills that are weak, it's the precursors to that. I think this is very widely accepted, and you of course see this as the R in Prim. We also have an element of this within the national curriculum itself. So even children as young as 5 to 7 should be taught to use logical reasoning to predict the behaviour of simple programs. They're at the key stage 1 of the national curriculum. What will this program do? Is the first question we'd want to ask our year 1 and year 2 pupils. Then, as they move up into upper primary, use logical reasoning to explain how an algorithm works, detect and correct errors in algorithms and programs. This is done by reading code. And then, of course, evaluate computational abstractions, evaluate the program that models the state and behaviour of real-world problems in physical systems, understand key algorithms that reflect computational thinking, and again, use logical reasoning to compare the utility of alternative algorithms for the same problem. We have these 2, 3, 4 ways of doing this, which is best, and that's a key stage 3 requirement. Why is binary search better than linear search? Is there in key stage 3. It's not something you leave until they have been taught big O notation. So we can reason about code ourselves, and this is much more fun if we're there in the room together and I say, what does this do? And then we see everybody's fingers tracing this in the air. The worst possible way of doing this is to say, okay, now run the program, see what it does. You want to dwell in that reasoning about the code space, in the reading the code, the running it on the machine in your head, before you actually ever run the code on the hardware in front of you. This is written in Logo, language which most of you probably haven't seen before, or if you did see it before, it's a long time ago. But you should have enough sort of familiarity with Turtle graphics to be able to make a prediction as to what's going on here. I can walk you through it, obviously. Forward 100, right 90, draws one side of a square. Doing this, or one side of a square. Drawing this 4 times gets us the square, and then we're going to do 10 squares, each of which is rotated round 36 degrees. 36 times 10 gives us 360, so we're back to the beginning there. With a little bit of luck, it's hidden. Oh, I don't appear to be able to let's just try deleting that. There you go. And we've got online logo interpreters if you want to play with that yourself. There it is back again. Okay. So we need to teach them how to solve problems. You cannot just jump straight into the reasoning about code. You've also, if you're going to ask them to write a program which solves a particular problem, that reasoning about the problem has to come first before you set your fingers on the keyboard or on the mouse or on the touchscreen, I guess. Computational thinking is the thought process involved. You know the quote there. And their solutions, so that the solutions are represented in a form that can be carried out by an information processing agent. I think widely accepted definition, despite what you will hear. We make inflated claims about this, but she's very clear, or Cooney, Snyder and Wing are very, very clear that this is about a solution that can be carried out by an information processing agent, by a computer. If we make inflated claims and say it's a general approach to solving all sorts of problems, then it's harder to justify that. It offers powerful tools for people who design computations. That alone is enough. It really is. Think of all of the things you could use a machine like this to do. Surely it's worth teaching people how to do that well. There's no need to make these exaggerated claims. Despite what we have perhaps read elsewhere. Okay. And so, even back in the days of logo programming, 1983 here, Roy P. doing the study that Papert didn't do. You take the class, split them into 2 groups. Half of them you teach to program in Logo. The other half just get on with their normal lessons. You then give them a test of what he called planning skills at the end of this period. And lo and behold, the group that had been taught to program in Logo didn't do any better on the test of planning skills at the end of this period. If you want them to get better at planning how to solve problems, at thinking skills here, then that's something that needs to be taught. As he said here, everybody could learn how to program, but it's only with accompanying instructions in thinking skills that development in planning skills may in fact be achieved, was his broad argument there. We talked a lot already about the Prim methodology, but it's also worth thinking about this idea of live coding, of standing up, and if you can stand up. Otherwise, you've got to sit down at your machine, and it's never as easy to maintain behaviour if you're sat down at the front of the room than if you're standing up. You want a standing desk up there, an old-fashioned 19th century school teacher's desk. Live coding seems to be a really nice way of doing it, effective pedagogical tool for learning programming, because you're not just showing them how to code, but you're showing them how to think. It's this teaching of problem-solving skills, the semantic knowledge that Schneiderman and Mayer refer to, which is so central to our discipline. Yes, remembering the indentation in Python and double equals for is equal to matters, but it doesn't matter nearly as much of how do you take this big problem down, break it into small parts, and by doing live coding in front of the class, interacting with the class as you do that, then you've got far, far more chance of modelling those thought processes. If you want to read the research, look up cognitive apprenticeship. It's what we're doing in a lot of subjects now, teaching them to think in the way in which an expert in that subject might think. And this matters. So, this idea of the most significant difference between the effective and the ineffective knowledge, it relates to their strategies rather than specifically to their knowledge. So in order to be effective as a programmer in learning how to program, then the strategies that they use for this is going to be really very, very important. And so by live coding, you can model that by showing them how you would do that, as I phrase it on the slide deck there, or at the top of the slide deck there. And so you've also got this idea of using the common patterns, of teaching them ways of solving the same sort of problem each time. You've seen the OCR coursework tasks as was, of how often they have to open a file, read something from a file, save it back to a file. You've seen the ones where they get a username and check that the password is correct. So teaching them a standard pattern for how you would do that sort of thing is well worth doing. And being quite explicit about this. So again, I can read from the quote there. Looking at what we typically do when writing programs, we realize we have canned methods for deciding what names to use and when, how to use them, standard way of reading the input, of writing conversions between different data representations, to name just a few of the tricks of the trade. And the Brooks paper here gives lots of other examples of the standard patterns that we would use. Let me illustrate this with one. So here's a little bit for you to predict first. So there's a program up on screen there. You might like to pause the tape if you can't do this straight away in your head, but have a look at the code. You should be able to tell me, if I were to ask you, actually hard to do on the video, what this program is going to do. And you should be able to run this on the interpreter in your head there and tell me what end result you expect. At this point, we would do the run bit of Prim. Here's one I prepared earlier. I'm starting to like Replit. More of this later on in the course. So here's my data. You're just going to narrate the whole thing here. I run the code and I get 18 out of it. So far, so good. What you can do, of course, is then take this skeleton of code and make it do something entirely different. Instead of finding the total from this, what if I wanted to find the largest number on this list? What's the simplest, the smallest number of keystrokes needed in order to modify this program to get something which finds the maximum from an arbitrary list like this? Well, I'm going to start by setting the max here. Now 0 is problematic, so I want to pick something as the initial max, which is too small. If we were inside float territory, I could do negative infinity. I'm not going to do that in my head here. Let's just take minus 999 as something smaller than every item on my list. There's an issue with this, which we could refine later. For the item in the data, if the item is greater than the existing maximum, then set the maximum to be that item. And then print out the maximum from my list there. So this is the same pattern. We set a variable up, we iterate over every item in the list, we update that variable, we output the variable when we're finished with the list. It's exactly the same thing at semantic level that I was doing with my adding up all of the even numbers. So, you're doing exactly the same thing here. It's exactly the same design pattern, but as an entirely different purpose to it. And teaching pupils this standard method for so much of what they're likely to see at GCSE is a sensible thing to do. Let's have a go at running this. Hopefully we get the answer 9 out of this. Thank goodness for that. Okay, and it has left as an exercise to the reader here. So Alt 3 on my keyboard. What if the maximum, the data is all less than minus 999? Okay, there is a way, all right, because you've got proper IEEE arithmetic in Python, but I can't remember quite how to do it now, and I'm not going to stop the tape just to look. Okay, we'll come back to some code later on. What's the next in the slide deck? So the accumulator pattern. And then this idea of breaking things down. Now, it's very, very hard to find research evidence which says a modular approach is better than an entirely imperative, just top-down, start coding, write spaghetti code. It's like it was back in 1980s with basic type approach. We have this, firmly embedded with our notion of what programming is create procedures, create functions, create create classes if you're working in an object-oriented language. And I think it's well worth, or most people working in the domain say, start this as early as you possibly can. One of my big criticisms of Scratch is there is no support for functions. Snap allows support for functions, which I think is yet another good argument for transitioning from Scratch, which they do in primary, to Snap as your block-based language for lower secondary before they move up into Python. So yeah, the modular approach, create functions, create small bits of code which do one particular thing, is kind of assumed now, and there's very little data out there or evidence out there to say this is better, because everybody knows it's better. Natalie wants to go off and do a study about this now, hopefully. So our modular approach, programmers must become skilled in writing subprograms, top-down programming, designing programs through procedural decomposition, writing general procedural abstractions via parameters. So all of this is good. How are students best taught to use subprograms? Specifically when and in what order should various subprogram features be covered so students can more easily understand and use them? Most people working in the domain say as soon as you possibly can. For the reasons that Pattis critiques in his paper from '93, students must learn good programming design habits early. Students need as much experience as possible writing subprograms, and so earlier is better than later. He takes a different position, but I think he sums up the argument of the vast majority of us very nicely there. This was at a time when Pascal was our programming language of choice. You've seen me do this sort of thing with things. So, we had that lovely AQA bulls and cows task here. Let me see if I can pop this up on screen for you. So you're familiar with this one from earlier on in the course. We had a look at both the bulls and cows task and that funny dice game thing. Here's the bulls and cows task. It gives us a very detailed specification of what we've got to do here. And if you read this through, there are all sorts of things like checking whether a particular guess is a valid guess or not, checking whether a secret code that the computer produces is a valid code or not, playing each turn, comparing the guess with the code. And we would break this down naturally into a number of procedures here. So here is my procedure for validating a guess. Here is my function for validating a guess. Notice it returns a Boolean value. It takes a string. Here, is it a string that I'm working with? I think it was a string that I was working with. It takes the string and compares that to, it takes a string, and if it's the wrong length, or if it's not a number, or if it already has something else in it, then in each of these cases it returns false. Otherwise we say it's a valid guess. You can see the code just as well as me. The point is that I'm creating small functions to do each of the important jobs within the code, and then essentially I've just got a single loop here which runs through the code. And I think that's quite an elegant solution to it, even if I say so myself. The dice game from OCR is a little bit harder to do, so my first thing here is to create a hash of passwords so that we don't know what the user's password is. We've got some sort of initialization stuff to read in the user table. And then again, I've got a function which gets the player's name. I've got a function here which operates each turn of the game. So you've got all of that going on here, and it's still very blocky, spaghetti-like code at the end there. But we've got, essentially a couple of functions that we're using. And getting them to adopt that habit early on seems to make a lot of sense. Okay. And that was the dice game, wasn't it? And one way of doing this is through the sub-goal labelling, of getting them to start with the problem and then identify the different things that they're going to need to do. And then, of course, once they've got those sub-goals written in, perhaps as comments, they can come back and start adding in the detail work there of what this function, how this function actually works. And that takes you down the unit testing approach of, can I test this particular function? Am I assured that that works? Okay, then we come on to debugging, and I've got quite a few slides on this. So here is Admiral Hopper, or she became subsequently Admiral Hopper. You'll notice that in her hand she is holding a piece of paper which says COBOL on it, Common Business Orientated Language, which was the language she designed. She created this language. She was one of the first people to cotton on to the idea of it was much, much more sensible to write a compiler specific for the actual hardware that you would run it on, and then you could write your program in the same language irrespective of what the hardware was, and the bespoke compiler would take that source code, the program written in the high-level language, and translate it into instructions that would run on that particular machine. We've obviously abstracted a few more layers since then, but this notion of the high-level language is something which we can credit, at least in part, to Grace Hopper's work there. So the story has it that Grace Hopper was working in the day when the switches inside computers, which are now on integrated circuits, were actually electromechanical relays there. So you have here an electromagnet. When current flows through the electromagnet, it pulls down this ferrous armature here, which makes a contact. Or it pulls down one of these things, which makes a contact. Here you go. It pulls down this bit of ferrous metal, which makes this contact here, which completes the circuit. So you have current flowing through one circuit, which controls the flow of current through another. You have one circuit controlling another circuit, and that still is the basis of everything that you have inside all of this hardware. Switches controlled by circuits themselves. So it's not manual switches. This is one bit of electricity controlling the flow of another bit of electricity, and this is still how integrated circuits work. So the story has it that back in the day when the switches looked like that, we have a little moth that flies in. I guess it must have been a bigger one than this, between the blades of the contact here. So when the electricity flows through the electromagnetic coil, it cannot close the contacts, and so it does not work anymore. How do you fix this? Well, you take your tweezers and remove the moth, the bug, as the Americans would call it, from between the blades of the contact there. And so Admiral Hopper writes in the notebook there, and I think there's some value in keeping a notebook alongside your machine on which you're programming. I love the squared paper here and the very high level of precision of whatever these numbers are meant to be. Anyhow, 1545, relay number 70, panel F, moth in relay. And first actual case of bug being found. It's a lovely story, isn't it? Now, okay, they were called bugs before this point, the errors in our machine worked, but it is, because otherwise she wouldn't have written about it in this way. But this actual, here is the bug that was causing it to stop working. Do you teach your pupils debugging strategies? Do your expert colleagues in school teach debugging strategies? I hope that they do. What is your debugging strategy? Do any of you, not seen anybody yet, work in computer labs where there's a little rubber duck stuck on the top corner of the monitor? Because one debugging strategy is to talk through your program to the little rubber duck there and explain exactly what it does, line by line, by reading the code and by describing it to the inanimate object. Very often your eye is drawn to, oh, that's what I meant to do, but this is actually what it does. So this rubber duck debugging is a well-documented strategy. There's like a Wikipedia article on it and everything. Another one is the idea of the wolf fence. How do you find a wolf in Canada? Well, you build a fence down the middle of Canada and listen to which side of the fence the wolf howls from. And then once you know which half it is, you put a fence across that half and then listen to which side of that fence the wolf howls from, and produce smaller and smaller and smaller spaces in which the wolf must be, because you can tell from which side of the fence the wolf is howling, and there you found your wolf. Same approach to finding a bug. Identify which bits of the code are working fine and where the problem is. Print statements, debuggers, and we'll do this for you automatically. automatically letting you watch variables and set breakpoints as the code runs. But a lot of us just do it by adding in print statements here and there, so we can see on a console or on the output what stage the program has got to and what value various variables have. It's a strategy which you should teach to them, which you should model to them, which you should encourage them to use. This is more general, but I love this sort of work on the pragmatic programmer. These are your standard strategies for fixing problems, for problem solving when you're working when you are working with a computer. I won't go through all of these now, but am I solving the right problem? Why is this a problem? I particularly like rely only on reliable things. Here you go, rely only on reliable things. So how do you, I can tell you stories about this. Does it have to be done at all? And in the case of your essays, yes, they do have to be done. Okay, what next? Phil Bagg has written very well about this idea of learned helplessness. Primary school teacher and advisory teacher for Hampshire. He says there's one of the things he noticed in his computing lessons was how many children would put up their hand and say, "Sir, I can't do it," or "Sir, it's not working," or "My program doesn't work." And this idea of they cannot fix this for themselves, they need you to go over and sort it out for them. I've not seen a huge amount of that happening in the lessons I've already been to see, but what do you do when it does? Is this something which is a problem with your classes in your school? And you can't solve this overnight. It's about culture, it's about mindset as much as anything else. It's about developing a positive attitude towards debugging, positive attitude towards problem solving, as Phil writes about here. Your role is to teach them how to teach them computing, is to teach them computer science, is in part to teach them how to program. Your role is not to fix their code for them. Fun as it may be to suddenly be able to go over and say, you're missing the indentation there. Don't do that. You're just programming for them rather than teaching them how to program. Draw their attention to it. Are you sure line 5 is right there? I think there may be a mistake in line 5, and indeed get them to read the error messages, which very often will say where the mistake is. Point out when they are exhibiting this learned helplessness. Don't touch their keyboards. Don't touch their mice. Not just to prevent the spread of the whole plague thing, but also so as to make sure that they're the ones who are at least learning something through thinking about it. And please don't let them think that the computer is out to get them. I used to make this joke about unless you were using Windows 8, but that's a few generations ago now, isn't it? And yeah, they can work together on these tasks, and I've seen some lovely lessons where you have encouraged that sort of teamwork approach to programming exercises. This all is part of this sort of growth mindset. Carol Dweck, I showed you some of Quentin Kutz's work around exactly this. Here's the paper that I was referencing then. Performance in a class test and the final exam of the course were better for those students who have been taught about growth mindset. Quentin wasn't just saying it's about how positive you are in your thinking. He also gave them really good advice on how to solve problems. And that, thankfully, is still online. So this is his crib sheet there. So the program has errors. What line is the error on? Read the error message carefully. Is it one of the common errors? Compare to an example in complex build it up gradually, and check your indentation. This is a common issue. These aren't misconceptions. These are mistakes. But I love Quentin's crib sheet here, and this is out in public. It's linked to from my slide. You can share this with all of your students. You can produce your own version in Visual Basic if you feel you need to. And Papert, of course, got it right back 40 odd years ago now. And he argues that if they had this attitude to fixing mistakes in other subjects, then the whole of school would work out better. They'd be more willing to have a go at things. They do that growth mindset thing of seeing mistakes as an opportunity for learning. It happens in our subject, or at least it does at the best of times. It shouldn't be happening everywhere in the curriculum, is Papert's argument, essentially. They should check their work as they go, and I'd reference here this idea of test-driven development, and we'll talk more about this on Wednesday, that you should write the unit tests for your functions, so you can check whether each function is doing what it should do. The test-driven development approach is a little bit more to it than that, and so you start with writing the test. What is it that the code should be able to do? Client comes along and says, can you develop this new feature? You have to understand exactly what the client means by that in order to write a test. It has to be specified very precisely in that sort of formal language that can run on the dumb machine. There's no equivocation about that. And then you should run the test first. So if your code already passes those tests, the test, then it's already doing the thing that the client has asked for. You can send your invoice straight away and you don't need to do any more work. It shouldn't do that because, it should already be doing the thing that they've asked for. So at this point you write your code. And, let's do that again. It should fail the test at first attempt because it's not doing what it's supposed to do. Then you write your code, you write your new function, you write your new module, and it should pass the test that you have already specified because you're a brilliant coder. If it doesn't, you come back and rewrite the code or debug the code, and sooner or later it will pass the test. At this point, you know it's doing the thing that you've been asked to do, so now you can send your invoice. But then there is always this refactoring. Can you do this better? Can you do this using less memory or in a shorter amount of time? Can you make the variable names more clear? Is the code as beautiful, as elegant as it possibly can be? Most people don't bother to go through that step, it seems. But this sort of cycle here of it should fail at first test, then it should pass because you've done it very well, and then you've got the opportunity to improve and refine on that. It is worth my saying now, I'll say it again on Wednesday, that this also applies to the other stuff, to the stuff that you do in your line of work. There is much to be said for when you are about to teach a new thing, write the test first. Give them the test. They shouldn't be able to pass the test at this point because you've not taught it to them yet. If they can, then they already know how to do this. Now, there's nothing wrong with a little bit more reinforcement of revisiting ideas that they've already covered, but you can do that differently. You've already brought it back to mind. They've already demonstrated that they know this because they've passed a test. You have just given them. It is wasting your time and their time to teach it to them again if they can already do this. So you can move on. Okay, go and do something fun with the rest of the lesson. If, on the other hand, they fail this test, well, then you've got to go and teach it. Give them the test again, or a slightly different test, and they should pass it at this time because they work hard and you teach brilliantly. If that doesn't work, then you've got to go and debug your lesson and find a better way of explaining it to them or making sure that they are paying attention as you're explaining this. But sooner or later, they should pass this. You then have that lovely bit at the end of the lesson plan form to refactor your work, to improve on what you have just taught. Think, is there a better, is there a more elegant, is there a more efficient way, a more effective way of teaching this? So a lot to be said for that. I want to talk a little about literate coding, of getting them to explain their work. And so one way of doing this is using something like the Jupyter notebooks to include both markdown text alongside runnable, workable code here. Here's something I used for my little introduction to programming course that I taught for students across the university last term. So, I've got, really, I hope, accessible text then, and then we get into the code, into the runnable code here, where we've got examples of this. I'm explaining what I'm doing here, all right. I can, I think, show you this. Yes, let me just bring this up so you can see what this looks like in practice. So there is, oops, let's move that down on the screen a bit. There you go. Will take a little while for Jupyter to power up here. Oh, I meant to say, I think there are moves afoot at Google to make Colab available again. There's another thing called Kaggle, which you could also use as a notebook interface if you don't want to install your own. And you know what this is going to do. So this is just demonstrating that we can take each variable in turn in the list there. You can do this for other things too. So notice I'm overloading the addition operator here. Evens is a list, an empty list to start with. It's just the same as we had earlier, where we've got this iterator pattern or accumulator pattern. And then I'm talking about the list comprehension syntax in Python, which does the whole thing in one go. And then I get on later to further examples of, oh yes, the lovely stuff which we did with images, which nobody had a go at. So I'm importing the Python image module and creating a new dark green, Roehampton green image with this. And this, of course, lets you play with, play around with the code, make something interesting or even beautiful. So my new pixel could actually be based on those numbers, X, Y, and let's take blue as 50 each time. And you get something really very different about it. And what about if I do 255 minus Y for this one? Okay, and it flips it around. So there's lots and lots of fun you could have there. And then I move on to the working with online images. So all of that, I've got code and text side by side. Now I'm using this as a teaching resource, but they could do the same thing, explaining what they're doing each time. Perhaps more accessible for the TikTok generation is creating the screencast tutorials of this. So here he is. This is the most popular video I have on the whole of YouTube, with 6,000 views and 165 likes to it, and some really very, very nice comments. So this was, you'll notice the date, 18th of March 2020. What was happening around 18th of March 2020? I'm using Python mode processing here, and I think I start off
throughout a population using Python mode in processing. Notice please I'm using processing here.
He goes on. Alright, so I'm subgoal labeling. I'm not talking at the moment because I'm
We're going to work on a 400 dot width, and we're going to work on a 400 pixel height.
And half an hour later, somewhere around here, I guess, we've got like runnable code. Okay, I'm trying to get to the right place. Is it 32? Somewhere around there. Okay, let's pop the playhead there and see where he gets to 32.
And let's put 200 of them in there together. Here we go. That's running quite slowly, isn't it? But it is running. Massive ramping up of the virus.
Okay, you've got the idea. So getting them to record the walkthrough video is a skill well worth teaching. You want them to be able to not just reason about code, but express that reasoning in human language. We've talked a lot about pair programming, and you know that it's a proven development strategy. Lovely paper by Williams and Kessler. I love the title because of the kindergarten thing, which is very Froebelian. All I really need to know about pair programming I learned in kindergarten. And, you know, the evidence that this is an effective development strategy with, you know, real life coders is really well documented. But of course, many of you will already have read that this is also a really good strategy for teaching programming. So of those who were in the pair programming, these metrics are all higher, and in most cases significantly higher in this pair column. So it had improvements on all of these things that they were interested in. And I think there is some evidence that it's even more supportive of the female students on these courses. So if you want to ensure that your programming classes or your computing course is more appealing to your female students, pair programming, providing a social environment in which people learn to code, may well be part of that. Okay, and it also seems to be particularly beneficial from those who start with lower prior attainment, and we've already spoken about that. Lower prior attainment is typically not the result of a lack of ability, but because of environmental factors such as coming from disadvantaged homes. Another opportunity which we have because of the deregulation of the programming element of GCSE is the chance for them to do some independent learning. Wouldn't it be lovely if more of your students at GCSE were willing to go off and teach themselves something, perhaps related to the spec, more excitingly still, not something that's not going to be on the exam. And there are such brilliant resources, as I'm sure many of you have already seen, It's worth my mentioning here that if you're still concerned about your subject knowledge in some aspects of computer science, there are fabulous resources out there to support you in developing that subject knowledge. I'm going to overload your Christmas holiday yet again. So yeah, you got an essay to write. Yeah, you need to spend some time, at home, away from school, decompressing after the term you've had. But you might also want to spend some of the time sort of developing your own subject knowledge. You know where your weaker areas are by now. You will easily be able to find things which will support you in developing those. And, come to me for advice, and just as you would want your pupils. I want to learn how to do this, or I want to learn about functional programming, please, miss, please, sir. Where would you point them? What would you recommend for them? There are brilliant resources out there online. I mention also teaching multiple development strategies. So usually we work in this sort of waterfall space of here is a list of requirements, your program should do this. You saw that with those old NEA tasks, the old coursework tasks. You then go off and design your solution. This is the computational thinking step of how am I going to solve this problem. Implement that as runnable working code. Test that it has worked, not test-driven development so much, and then there's not really a maintenance phase in these coursework tasks, but you might want to move into the documentation phase at that point. A lot of software doesn't actually get written this way. That seems, just peculiar to public sector procurement. It's not a particularly effective approach. A more iterative approach makes a much, much more sense. Okay, so here you design your program, then code it, then test it, then evaluate it. Okay, it's more than just testing the code to see that it works. Step back, look at the way you've solved the problem, and then go back in. What features could we add to this? How could we do this better? And then go back through that loop as many times as you can, really. It's worth saying that a lot of teaching feels like this at times. Here's the exam specification. Here's my scheme of learning. Here's how I'm going to make sure that my GCSE class cover the exam specification. The implementation is done by you as the teacher in the classroom. There's plenty of verification, testing whether they have learnt the thing that you've been taught. I'm not quite sure what maintenance looks like, but maybe it's just making some tweaks to this. Is this now still fit for purpose? But of course, this iterative approach is what we're really encouraging you to do. Yes, you're planning your teaching and you're assessing using assessment data to inform your teaching, because we then go back through the loop. Never laminate your lesson plans. Think about how your assessment data from the lesson that you've taught suggest areas in which you need to improve it, in which you need to plan better. And Mitch Resnick has this as... didn't work, did it? Okay. Does that work? Okay. Mitch Resnick has this at the heart of the Scratch philosophy of education. You start with an idea, you create something, you play with it, you share it with others, you reflect on that, and then you go round the loop there. I think that's a really nice way of capturing another way of thinking about iterative development. Out of this, of course, grows notions of agile software development, that was the stuff on the left, which comes from that waterfall or indeed iterative approach, following a plan, negotiating the contracts, documenting everything, having the right processes and tools. Does this feel very familiar to what you're doing in school? These things do matter. Nobody is saying these things aren't important, but the Agile software movement or software engineering movement recognised that actually there were more important things about responding to change, about collaborating with your customers in their context, about having, working software. Working software is so much more important than comprehensive documentation, and indeed focusing on the individuals and interactions. And when you think about your line of work, are you excited by the stuff on the left here? Are you much more excited about an approach that's characterised by the stuff on the right here? So yes, we could talk about Agile software development, but you might also want to start thinking about what does Agile teaching look like. I think this is very similar to the adaptive teaching that we talked about a couple of weeks back. Responding to the change in the lesson. This happens. They say this. They don't understand that. You don't follow your plan. You respond to what's just happened. And, this is my mark of when you are, ready for your QTS badge. When rather than following the lesson plan that you've prepared for me and for your mentor, you respond to the change of what happened during the lesson. You can react immediately to the actual difficulties they have, rather than, oh, I'm sorry, we'll talk about that another time, I need to press on with this. If you are, rather than, some sort of very sort of formal behaviour management, you actually see yourselves as collaborating with your pupils. Yes, what matters is not your lesson planning, but whether, sorry, I never said that, okay, but whether they have learnt the thing that you set out to teach them. This is fundamental to our job. And yes, of course, the processes and tools of our trade matter, but so do the individuals and interactions. And at some point, you might want to think, well, what comes after even that? And so the software craftsmanship philosophy says these things matter, but these things really matter. Okay, it's not about just responding to change. It's also about making sure this is the best possible lesson. And yes, working alongside them matters, but working with others matters as well. Working software that this lesson worked, they learnt the thing that they were meant to, matters, but having the best possible lesson to teach this idea of really being proud of your craft. And of course, focusing on the children in the room with you is really important. That matters, but so does your participation in the wider community. It was so lovely to have so many of you stay on last Wednesday and meet some of our local teachers there. I want to talk about contexts. I'm coming to the end very, very soon. Don't worry about the context in which we do this. When David Brown was the lead HMI for computing for our friends at Ofsted, he put slides up which included the outstanding computing only happens when the contexts are relevant to pupils' lives. And, this was prescient of him, 2014, and it's only now that we're starting to think about what is a culturally relevant curriculum for computing and reflect the increasing use of computing in the world of industry. Excellent links are forged with other agencies, the wider community, not just doing GCSE programming tasks. Wide range of enrichment activities to promote pupils' learning and engagement with the subjects. Links with other subjects are productive. How many of you have got that working well? How many of your mentors have that working well? Pupils are expected to use computing knowledge, skills and understanding in realistic and challenging situations. What do they look like? My favourite example is Apps for Good, and forgive me that this is from 2014, but it was a really good year. Okay, so what do we have here? Inspire Workshy kids and flatmates to do their share of the housework. A little app which there says, tracks how many tasks, jobs around the house you've done. And one of my favourite ones is using the public data set about where crimes happen. And rather than finding the fastest route between two locations, finding the route between two locations, which takes you through the fewest areas where violent crime has happened. You could imagine parts in London where that really would matter. And then this whole thing about how do you keep track of pocket money in a day and age when we don't actually use coins anymore. And again, 2014, they were prescient, weren't they? We used to have this lovely Young Rewired State thing. Emma Mulqueeny, who ran this, I think moved on to other more exciting things. She's working for SUSE, one of the big Linux distros now. But Young Rewired State brought young people together with software engineers working out in the public sector to do interesting things with big public data sets. What can you do over the course of the weekend with youngsters interested in coding, working with professional software engineers and big public data set? My favourite here was the pumps thing. So use a machine learning algorithm to detect the letters on a car's number plate, look that up very quickly in the DVLA's database, check whether it's a petrol or diesel engine car. This was in the days before many EVs were around. And shut off the pump if it was the wrong sort. So you attempt to put diesel in your petrol engine or petrol in your diesel engine car, and it won't let you because it's read the number plate and knows what sort of engine the car has. That would have saved me £100 in a couple of hours on one particularly embarrassing occasion. And of course, the platform on which you develop, if you want a place on the computer science course at Cambridge, a bit late for you guys now, then one of the things they strongly advocate is get yourself a Raspberry Pi and learn Linux using that. If you've not yet put your Christmas list together for what you would like from Santa and don't yet have a Raspberry Pi, then this is a really nice way of getting into another environment different from your Windows. And of course, the BBC Microbit will return to both of these platforms later in the course. Finally, this idea of developing fluency. The whole point of this is to become fluent in how these machines work to achieve a degree of mastery within this particular domain. That's not going to happen by the end of GCSE, but the purpose of this is to be thinking about this, is to understand what's happening here. Sorver's paper on the misconceptions of computer programming I think this was a master's dissertation originally. Programming Misconceptions Studies Theories of Mental Models, Constructivism, and Research on Learners' Way of Experiencing Programming, and Theory of Threshold Concepts all lend support to the idea that beginners' programs need to learn about one or more notional machines. They need to form a mental model of how the machine in front of them operates. You can do this experimentally, you can do this through didactic instruction, but central to our purpose here is forming a good understanding of what the computer will do and how it works. I will end with Bill Lau's words here. The goal is to allow young people to become so fluent in computer language that they become coder poets by learning their own way, creatively coding with economy of expression and art. This is about creative expression. Yes, we build a model in our head by building something out in the world, but the thing that we build in the world does matter. Take an idea, be creative with it, make something of which you're proud. I think the same applies in our line of work as well. You know, your mastery in as a teacher is in part about this notional machine. How do pupils in front of you, how do young people learn things? What is your mental model of the learning process? But also the creative expression of that teacher poets, of making the best possible lesson. I have spoken too much, but I'm going to stop the recording now and upload this to YouTube for you to watch. Okay.